So we are going to do a couple of examples of the Gram-Schmidt process. And what it does is it takes two linearly independent vectors and it turns them into two orthogonal vectors. So we like to have a basis for a subspace, but it's better if we can get an orthogonal basis. So we're just going to work through the Gram-Schmidt process first with two vectors, and then we'll do one that has three vectors. So first is I'm going to name these. We'll call this x1 and x2. We just want to verify that these guys are linearly independent. So I put these vectors in a matrix A, and I'm just going to row reduce these and make sure that I get two leading ones, and I do, right? So that means they are linearly independent. You can also tell by, if you only have two vectors, if they're not multiples of each other, then they have to be independent. Now, if I take the dot product of x1 and x2, I get 24 plus 0 plus 6. That's 30, right? So these are not orthogonal. So what I want to do is find two orthogonal vectors that are going to be in the same subspace. So we'll say W is the span of x1 and x2. Okay, so I want a vector that's still in W, but is orthogonal, two vectors that are orthogonal to each other, and then I'll replace x1 and x2. So we want to find, say, two vectors v1 and v2, and we want two vectors such that v1 dot v2 is equal to 0. So we want them to be orthogonal, and we want the span of the two vectors to be the same as the span of x1 and x2. So we still want to span them and get the same subspace W, but we want them to be orthogonal. And if they're orthogonal, we can go further and make them orthonormal if we want to do that. All right, so here's the process. So the first vector v1 is easy. You just let it be x1. So that is that's the good news. Okay, so to get the second one, we're going to take x2 and subtract this x2 dot v1 over v1 dotted with itself times vector v1. And this should look familiar, right? This is how we did projections. We're subtracting this projection, and it's going to give us an orthogonal vector, right? So remember that vector z, we added that vector z in the projection, and we got our vector. Well, here we're going to subtract this to find z, and that orthogonal vector, we're going to do it so that we stay in the subspace though. Okay, so we're just going to plug these into this formula. So x2 is 8, 5, negative 6. And then we're going to have a fraction with these dot products. And we're going to multiply by v1. v1 is just x1. So the numerator here is x2 dotted with v1. And v1 is x1, so I just need to dot product these two together. So I get 24 plus 0 plus 6, so I already did that one. I get 30. And I need to dot product v1 with itself. So v1 is x1. So if I dot product v1 times v1, I get 9 plus 0 plus 1. That's equal to 10. So this fraction we can reduce to 3 over 1. All right, so I'm just going to do the math here. I like to multiply these constants inside the vectors. I like to multiply the negative 2. So I'm going to multiply negative 3 inside this vector. So I'll get negative 9, 0, and positive 3. And then when I add these together, I get negative 1, 5, and negative 3. So that is my vector v2. Okay, so now let's verify a couple of things, right? So one thing we need to be true is we need v1 dot v2 to be 0, right? This guarantees orthogonality. So here's v1 and here's v2. So let's dot product them. So I get -3 and then 0. And then -1 times -3, that's +3. And that is indeed 0. So it does check out. We also need both of these vectors to be in the subspace. So I know x1 is, right? Because it's the span of x1 and x2 will include x1. I need to make sure that the span of v1 and v2 is also the same thing as the span of x1 and x2. So what I'm going to do is make a matrix with x1 and x2 as the first column, and I'm going to make v2 the third column. So let me type this in here. So you could say I'm augmenting x1 and x2 with v2. And if I get a solution when I row reduce this, that's going to mean that v2 is just a multiple. It's just a linear combination, not a multiple, but a linear combination of x1 and x2. So that means this v2 is in the same subspace. It's orthogonal and linearly independent with v1. That means those two together make a basis for the subspace. So my orthogonal set is going to be v1, which was x1, and v2. Right, so the problem says produce an orthogonal basis for the span of the following vectors, and that's what we did. All right, so let's do one that has more vectors, and it's going to just take one extra step here, but we want to find an orthogonal basis for the column space of the following matrix. So let's let this column be x1, this be x2, and this be x3. If I span those three, these are vectors now. If I span these, I get the column space of A, right? This is A. That's what the column space is. You take all linear combinations of the columns. Okay, now, in order for Gram-Schmidt to work, you've got to make sure that your vectors are linearly independent already. So let's make a new, let's clear this out. New matrix A, it's going to be 4 by 3. I messed up there. All right, so I have my matrix A, and if I row reduce it, I want to make sure that my columns are independent, and they are. So I get a leading one in every column. That means they're independent. So if they're independent, then I can use Gram-Schmidt to create my orthogonal vectors that are going to go into my new basis. Okay, so v1 is x1. Same thing. You get a freebie here always at the beginning. Kind of start with the first one. It's going to be the same. v2 is going to be x2 minus x2 dotted with v1 over v1 dotted with v1 times vector v1. All right, so we'll just work through this. So here's x2. We have a fraction with the dot products, and then times v1. v1 is x1. All right, so x2 dot v1. Remember, v1 is x1. So I just need to dot product x1 and x2. So I'm going to, let's just do this here and I'll write down all these things. So negative 15 plus 1 minus 5 minus 21. So I'll use my handheld calculator here. Negative 40. So this numerator is negative 40. All right, and then the denominator is v1 dotted with itself. So that's x1 dotted with itself. So I'm going to get 9 plus 1 plus 1 plus 9, right? You just square these and add them up. So that's 20. All right, so these two negatives will cancel. We'll get a plus, and the fraction is going to be 2. 40 divided by 20. So I'm going to add x2 to 2 times x1, or 2 times v1. So it's going to be 6, 2, negative 2, 6. We'll just add these together. I get 1, 3, 3, negative 1. So that is v2. Okay. So at the end, we'll check orthogonality and all that. So let's go ahead and do v3. So what do you do with v3? It's going to be the same thing, except we're going to add, we got to make sure that we're orthogonal to both v1 and v2. So we're going to start with x3, and we're going to subtract x3 dot v1 over v1 dot v1 times v1. So there's one projection, and then we'll subtract the other x3 dot v2 over v2 dotted with itself times vector v2. So this is going to ensure orthogonality with both v1 and v2. And if you had a fourth vector, you would have 3 of these and so forth, right? So this can get really messy if you have a lot of vectors that you have to deal with. But here, we only have 3. It's not terrible. All right, so what is x3? So I'll look at the top. So third column here, so it's 1, 1, negative 2, 8. Then minus. I have a fraction times v1. v1 is x1, so 3, 1, negative 1, 3. Minus another fraction. And then v2, that is 1, 3, 3, negative 1. Now we just need to do these dot products. So now what is x3 dot v1? Well, here's x3 and here's v1. So let's dot product them. So I got 3. Here, I'll write it down over here. I got 3 plus 1 plus 2 plus 24. That's 4, 6 plus 24. That's going to be 30. v1 dotted with itself. So it's going to be 9 plus 1 plus 1 plus 9. So that's going to be 20, just like we did before. And then we have on the second fraction, we have x3 dot v2. This is v2. So x3 is the first vector here, and this is v2. So let's dot product them. So I get 1 plus 3 minus 6 minus 8. Negative 10. and V2 dotted with itself. So this is V2. So it'd be 1 plus 9 plus 9 plus 1. That's going to be 20. So let's simplify a little bit. So I'm going to say plus negative 3/2 times V1. It's going to be plus positive 1/2, right? 10 over 20. These two negatives are going to cancel. Times 1, 3, 3, negative 1. Then I'll multiply those inside. So this is negative 9/2, negative 3/2, positive 3/2, and then a negative 9/2 again. Now multiply the third one by 1/2. 1/2, 3/2, 3/2, and negative 1/2. All right, so I'm going to change these entries into fractions over 2 so that we can just add fractions over 2 with these other vectors here. So 1 is going to be 2 over 2, 2 over 2. Negative 2 would be negative 4 over 2, and then 8 will be 16 over 2. And now I just need to add these together. Got 2 minus 9 plus 1. So that's going to be negative 6 over 2. I've got 2 minus 3 plus 3. So it's going to be 2 over 2. Negative 4 plus 3 plus 3. That's going to be 2 over 2. And I've got 16 minus 9 minus 1. That's going to be 6 over 2. So this comes out to negative 3, 1, 1, 3. So that is our V3. Okay, so let's write down our vectors here. So V1, they're all very similar, right? V1 is 3, 1, negative 1, 3. V2 is 3, 1, 3, 3, negative 1. And V3 is negative 3, 1, 1, 3. So what we need to check now is to see if these are orthogonal to each other and make sure that they're all in the same subspace so that when we span them, we're going to get the same set. So let's try V1 dot V2. So I get 3 plus 3 minus 3 and another minus 3. So that's 0. So that works. But V1 dot V3, negative 9 plus 1 minus 1 plus 9. That's also 0. And then last, what about V2 dot V3? Negative 3 plus 3 plus 3 and minus 3. That's 0. So they're all orthogonal to each other. So now let's just check to see if they're all in the same subspace. Now I know V1 is because it's X1, right? So it has to be. Let's see if I can edit this. Let's make 2 more columns. We're going to put in V2 and V3 here. All right? So let's just look at this guy here. So when we row reduce A and I'm augmenting here, you can see I don't get any no solutions, right? There are no solutions here. That means both V2 and V3 are in the same, they're in the column space, right? So if they're in the column space and they're orthogonal and they're linearly independent, they make an an orthogonal basis. If I want to make them orthonormal, I can normalize them by dividing by each magnitude, right, and make them unit vectors.